Hey, so we said our goal was to count atoms by weighing them. So one of the things that would be really handy, what it really be handy to know if you're going to count things by weighing them would be how heavy an atom is. And that would be atomic mass. Ever look at that? The mass of an atom. So, if somebody asks you a question like, how heavy is an atom of oxygen? The 16th, yeah. How heavy is an atom of oxygen? You should probably say, hey, that's a trick question. Say, well, why is that a trick question? Well, how heavy is a car? Depends on which car you pick, right? Remember, Dalton was wrong. There is not one kind of oxygen atom anymore. There are several kinds of oxygen atoms. And since there's several kinds of oxygen atoms, you can't ask how heavy is an oxygen atom because there's several kinds. Okay. But when I'm talking about an oxygen atom, am I ever going to have just one of them? The only place you can get one at a time is in that mass spectrometer that bends them, right? That's the only way you can get one at a time. Otherwise, you're going to get a mixture of all the weights. So what we're really concerned is not with what one atom weighs, but what the average atom weighs. So when we talk about atomic mass, we're talking about averages. So Johnny had some rocks at our bell work today. Some of them weighed 50 grams, some of them weighed 60 grams. How much did the average rock weigh? Look, 52 grams, right? Everybody got 52 grams for that? So the average rock did not weigh what any of the individual rocks weighed. If they weighed 50 and 60, how come I just didn't divide it in half? Why didn't I pick 55? There were more 50s than 60s, so I have to take into account not just how heavy they are, but how many of each kind there are. So I got it based on the abundance of each element in nature. Yeah. Oh, sure. Let me take it. Yeah, that was from this weekend. So I need to take into account not just how heavy each individual kind of oxygen atom is, but how many of each kind I have. Because there's some that weigh 16 and some that weigh 17, but there's a lot more that weigh 16 than weigh 17. Okay? Hey, the next thing. We don't want to use grams. I mean, that homework last night showed you why you don't want to use grams. Look at those numbers. Even if I have 120 million atoms of copper, it's going to weigh 10 to the minus 14th grams. Okay? Grams are just too small. Can't use grams. They're too small. I do not want to do math with numbers like 1.27 times 10 to the negative 14th all the time. And neither do scientists. They're lazy. So we got two issues. One, we got different kinds of oxygen atoms that come in different amounts. Two, we don't want to use grams. Okay, so we're going to solve the grams problem first. Okay? So to measure atomic mass, they said, I don't want to measure in grams, so I'm going to come up with a new unit. Okay, and the new unit we want is the unit for measuring atomic mass, so we are going to call it the atomic mass unit. That's the laziest name ever. The unit for measuring atomic mass is the atomic mass unit. So they had to pick something to be the unit for atomic mass. And chemists picked 1/12 the mass of a carbon-12 atom. One-twelfth the mass of a carbon-12 atom. There had to be a reason for picking that. It's not that's not something you come up with randomly. In fact, physicists came up with their own. There was two periodic tables for a while. The physicist used 1/16 the mass of an oxygen-16 atom. Okay. So eventually we convinced the physicists to go our way, but there were two periodic tables for a while. Why would you pick carbon-12? And why 1/12? Well, what pieces are in the nucleus of carbon-12? Well, it's number 6 on the table, so it's 6 protons. So if it's got 6 protons and its mass number is 12, it's got 6 neutrons. And there's also 6 electrons, but remember, electrons don't show up until the 4 sig fig when you're talking about how heavy atoms are. Like throwing a bottle of water in the car doesn't change its weight significantly. Right? So for the most part, I got 12 pieces. And those protons and neutrons weighed almost the same amount. Right? They're very tiny difference in their weights. So if I take those 12 pieces, the weight of 12 pieces, and divide by 12, I get about the weight of 1 piece. So an AMU is about the mass of 1 proton or 1 neutron. So the atomic mass unit, they picked something that was about 1 proton or 1 neutron. So did the physicist. They picked oxygen-16, 1/16 of an oxygen-16. Oxygen's number 8. 8 protons, adds up to 16, 8 neutrons. Divide, you get 1 proton or 1 neutron, about 1 proton or 1 neutron. There was enough of difference along the way that we could tell the difference between the two tables. That 4 sig fig was off for a bunch of them. Okay, now, so that's going to solve our problem about, we're not going to use grams, because each isotope has its own atomic mass. And that atomic mass is going to be really close to the mass number. Because the mass number is the number of protons plus the number of neutrons. And an AMU is about a proton or a neutron. So if you've got an atomic mass of 238, you're going to expect that that atom is going to weigh about 238 AMUs. Might be a little bit off because it's not exactly 1 proton and 1 neutron, but it's going to be right next to 238. Maybe 237.9, maybe 238.1, but somewhere in that range. Does that make sense? So we're going to have to get the average, and they're not going to tell me I've got one rock that's 60 grams and 4 rocks that are 50 grams. We're going to have much bigger numbers. So instead, they will tell us the percent abundance. And remember what the graphs looked like for those mass spectrometers, where it was just a series of lines about how tall each one of those was how many of those atoms you had? Well, how tall that line is what percent is of the total line. So they take the percentages straight off that graph. So you use a mass spectrometer, separate into half, and that's how you get the percentages. So I'm going to teach you a new way to calculate averages. Okay, this was your Bellwork problem, right? Okay, so you don't have to do any of this math. I just want to show you how you could have done Johnny's problem with percentages instead. why percentages work. I don't like to tell you math and just say, oh, this works, trust me. I want to prove to you it works. Okay, so I bet you that this is what you did. You don't have to copy this down. This is probably just about. You said, oh, I need the total mass. So I had 4 rocks at 50 grams and 1 rock at 60 grams, so I had a total of 260 grams. And then I took that, to find that average, I took the total and divided it by 5. I got 52. Everybody okay with that? So I'm going to take this math and do a couple of algebra steps to show you how you could have done it with percentages. Okay, so first I'm going to do backwards of what you always do with fractions. I'm going to split the denominator. Usually you get to a common denominator so you can add. I'm just going to take that 5 and put it underneath both of them. If you don't believe me, we know the answer is 52, right? So 40 times 50 is 200 divided by 5 is 40. 1 times 60 is 60 divided by 5 is 12. 40 and 12 makes 52. We are still at the same value. This still adds up to 52. Okay, so normally you put them over a common denominator so you could add. I just took that denominator and separated it. Now I'm going to regroup. And I'm going to put the 5 under the 4 and the 1. Okay to do that? Now I'm going to change it to decimal points. 4 out of 5 is 0.8. 1 out of 5 is 0.2. Okay, so now we've got to think about our rocks in terms of percentages. What percent of the rocks weighed 50 grams? 80%. Okay. And 20% weighed 60, right? 80 divided by 100% is 0.8. 20% is 20 divided by 100 is 0.2. So to figure out an average, all you have to do is take the percent and turn it into a decimal and multiply it by that piece. So I took the 80% times the 50 grams, the 20% times the 60 grams. I'm still going to get 52. Because 0.8 times 50 is 40, 0.6 times 2 is 12, 40 and 12 is 52. Look at this. Okay, so now do you believe me that you can use percentages to find averages? Hopefully you believe me because that's how I do your grades. When I say 50%, that 25% of your grade is homework, I take your homework average percentages and I multiply it by 0.25. The 5% that's bell work, I take that bell work and multiply by 0.05. And I do that with all of those and I add them up and that's what your grade is. Using percentages to find an average. Okay? So, to figure out the average using percentages, take the percent as a decimal times the mass, plus the percent as a decimal times the mass, plus the percent as a decimal times the mass. You keep adding pieces as long as you have that many kinds of atoms. If you have three kinds of atoms, you'll have 3 percentages. You'll need to add 3 numbers. First you multiply, then you add, which means you round after you multiply. Right? Because we're changing sig figs rules. So you're not going to be able to just stick these in your calculator and push one right after the other. You're going to have to stop to write something down in the middle. Because you've got to round off all the masses along the way. Does that make sense? So that's the math we're going to do for how to find the average atom. So, calculate the atomic mass of copper if copper has 2 isotopes. 69.11% has a mass of 62.93 AMUs, and the rest has a mass of 64.93 AMUs. What is the mass of the average copper atom? We know the average has got to be between 62.93 and 64.93. Right? Because the average has got to be between the highest and the lowest. But what's it going to be? So what does this look like? Okay. We said the average is going to equal the percent as a decimal. The first percent I have is the 69.11, and to turn that into a decimal, I make it 0.6911. Multiplied by the 62.93 AMUs. My unit is AMUs. And to that I want to add, well, I know the other one weighs 64.93 AMUs. How am I going to figure out what its percentage is?
1 minus 0.694.
Yeah, I can either subtract the 0.6911 from 1 or the 69.11 from 100. So 30.89, which is 0.3089. Now I know I want to do that addition, but I don't want to add those. No, I don't want to just push those buttons because I need to know where to round. So 62.93 times 0.6911 equals a whole screen full of numbers, and that's 43.49 AMUs because they both had 4 sig figs. The percentage had 4 sig figs. Okay. 0.3089 times 64.93 is 20.06 AMUs. Now I can add those together. It's 5, 5, 3, 63.55 AMUs. So that 63.55 AMUs is what the average atom weighs. You know, there's a way to check. Because we had something we labeled average atomic mass. What was the number on the periodic table? You look up copper, it says copper is 63.55. That's how they got the number, is they took into account how many of each isotope there was. And that's why some copper atoms weigh 62.93, some weigh 64.93. The average one weighs 63.55, which is closer to 62.93 than 64.93. It's closer to 63 than 65, because there was more of the 63 than the 65. And this right here, that's copper 63. And this is copper 65. So I said the AMUs are pretty close to the mass numbers. The AMUs are close to the mass numbers. Sometimes a little higher, sometimes a little lower, but they're always really close. Really super hard math? Oh. Okay, how do they make it harder? They give you more isotopes. Okay. Magnesium has 3 isotopes. Almost all of it's magnesium-24 with a mass of pretty close to 24. Ten percent is magnesium-25 with a mass close to 25, and the rest is magnesium-26 with a mass close to 26. What is the mass of the average magnesium atom? Well, the average equals 0.7899 times 23.985 AMUs plus 0.1000 times 24.986 AMUs plus my third one, well, 78.99 plus 10 is 88.99. 100 minus 88.99 is 11.01%. Got it up to 100, so it's 11.01. So that's 0.1101 times 25.983 AMUs. Okay, so I got both multiplying and adding, so I got to round two different times, right? So 0.7899 times 23.985 is 18.95. There's 4 sig figs. I don't need a calculator for the next one. 2.497. I can do that one in my head. Move the decimal place over once. We like tenths. It's 9, sorry. I rounded up the wrong one. 9. I like that. The strange thing is it won't show up in our answer. It's 2.861 AMUs. So adding that up, that's 5, carry the 1, 16, 5. I'm adding things up that don't line up. Stop that. So 18.95 plus 2.499 plus 2.861 equals 24.31 AMUs. Which shouldn't be a big surprise because it says right there, magnesium's 24.31 AMUs. That's where they got the numbers. So it should work out okay. Now, so the general rule we can do though is if they don't give me this number, would my answer have been hugely different if I'd used 24 instead of 23.985? No, it would have been about the same. 23.95 is pretty close to 24, right? So unless you're told otherwise, if you're not told, the mass numbers and AMUs. That's how heavy that is. So we expect, the only one that's absolutely true for is carbon-12 weighs 12 by definition. But all the other ones, I can expect sodium-21 to weigh 21 AMUs. Probably going to be just a little bit off, but I'm going to be really close by saying 21 AMUs. Okay. The most common mistake people make in doing this is changing the percentages. Because sometimes you'll have a percentage like 0.35%. You have to move it twice every time, so it's 0.0035%. Percent means divide by 100. Right? So if it says percent divided by 100, move it over twice every time, no matter where it starts. Does that make sense? Okay. I could talk about it all day, but that's because I know how to do it. The goal is for you to know how to do it, though, right? So here's something to practice with. I don't think I gave you the nasty one with 7 isotopes. Well, I showed you chromium had 6 the other day, right? Oh yeah, you can take all the answers, put them on a periodic table, write them down, and I'll mark them all wrong. Because no work, no credit. So the work should look a lot like the work I showed you. Don't forget the AMUs. I know it's 3 letters for a unit that's so much to write. It's a fate worse than death. And I didn't give you 100 of them, I gave you 8. Okay, so, no, don't be mean. That's my job. They pay me a lot of money to be mean. It's not your job. You don't get to volunteer. This is a union shop. Okay, it's a union shop. I'm paid to be mean. You're not allowed to be mean. It's a union shop.
So based on the last thing you told us for these products, can we just use like
No, because I did give you exactly what they were. But we're going to run sometimes like in textbooks where they won't tell you what it is. They won't give you that decimal number. And you say, where did they get that decimal number? It's, yeah. If they gave it to you, why would you throw out useful information? Yeah, so that's how many sig figs it has. Yeah, but no, the percentage is also a measurement. So the percentage is a measurement, the AMUs are a measurement, so you got to do sig figs when you're multiplying. They both have sig figs.